Understanding the principles behind OOP, that is, inheritance, interfaces, encapsulation, and polymorphism, are important for you to build well-structured applications. So let's take a straightforward look at some of these concepts. The idea, first and foremost, is sort of based on this notion of a class. A class encapsulates a concept. That could be a real thing, such as a table or a customer, or something entirely conceptual, like a game round. But the idea is, I want to do two things inside of my class. I want to be able to capture the relevant state and provide an implementation for the behavior. What is it that this thing can do? So I may have some class defined called X. If I have another class that is very similar to X in terms of what it represents, then depending on what I am trying to accomplish, X may serve as a base class for my new class Y. The idea here is that everything that is in X will be inherited by Y. Therefore, X is, or rather Y is X. So any object that is of type Y can be used whenever an object of type X is expected. So we'll see what this looks like in a second. Now, in addition to classes, in most OOP environments, you can also define something called an interface. Now, the idea of an interface is to capture behavior. In modern implementations of programming languages, you can think of that as methods or functions. But they don't provide the implementation. They just provide the list. It essentially serves as a contract. The idea is we define an interface, so we'll call this interface A. And what you're doing when you define an interface is you're specifying a guarantee. You're essentially saying, if any class, say class X, implements interface A, then one of two things must be true about X. Either X has provided an implementation for all of the functions defined in interface A, or X is abstract, meaning it's incomplete and you cannot actually create an object of type X. So one of those two things must be true. So if you have an object of type X, then that clearly tells us X is not abstract. So I have a guarantee that any function defined in A will have an implementation in the object of type X. So if I take the object name X dot whatever, and I can specify and invoke the function that was defined in A, I should get some behavior. I should get something happening in my code. So here we have essentially two classes and an interface. Class X is serving as the base class of class Y. So Y is inheriting from X, and X has implemented interface A. So at this point, what we have is any object that is of type X will be of type X and of type A. Additionally, any object of type Y will be of type Y, of type X, and of type A. So a class can extend another class, and a class can also implement an interface. But we can go deeper. So most programming languages, OOP languages, in addition to allowing classes to inherit from other classes, they also allow interfaces to inherit from other interfaces. So it means I can have an interface B that can, as a starting point, extend or inherit from interface A. Interface B will inherit all defined behavior in A as a starting point. You can thereafter add additional functionality or define additional functionality for B. Similarly, when Y extends X, you can add additional functionality for Y, sort of differentiating them. So let's then do this. Let us say Y has implemented B. Well, what can we say about Y in this case? Well, in this scenario, Y is almost like a super object. That is not a technical term. Because Y, an object of type Y, in this scenario, is of type Y, of type X, of type A, and through direct implementation, it is also of type B. What's more is, even if we did away with this relationship where X implements A, we will still have a scenario where Y is of type X, B, and A. Because, of course, Y is of type A because it has implemented B, and B has in turn extended or inherited from A. So Y is of all of these types. So what does that look like in an implementation? Well, let's do something very simple to sort of bring this to life. So X, Y, A, B are very general for a conversation, but for an implementation, let's look at something a little more concrete. So let's say we were defining something called an animal. And we could go much lower, obviously, but let's start with an animal. And inside of animal, we define whatever identifies animals, whether that's, again, we don't want to go too deep. We don't want to get into mammals versus other types of animals. We'll just say an animal. And Y could then be some animal type. So it uses animal as the base, and we could say that Y is a dog. So a dog is the animal. So inside of animal, I would expect to find all the things, all the state information, all the data related to animals. Maybe that would be the genus, maybe that would be just the name you want to give to the animal, etc. A dog would then be a specialization of that. So it would be a specific name, specific genus. Then as far as interfaces go, we can think of things that might be specific to a animal. Maybe we don't need to look at classes, interfaces extending other interfaces right now. So let's ignore this part for now, and let's just stick with this simpler relationship where an animal or the animal class implements some interface. So let's just say this interface is communication. So the communication interface. The idea is every animal has some mechanism for communication, whether that's true or not. This is not a biology course. This is true in our program. So inside of our code, we'll have some interface that defines what it means to communicate, and that may simply be one or more methods. So let's see what this can look like in practice. So we'll start by creating our animal. So let's create an animal class. And here we can have whatever data we would like. For now, we'll just keep it simple. We'll say that this is a name. Because this is Kotlin, we have a few options in terms of how we initialize or how we choose to declare our properties. In this scenario, I'm saying name is not null, and we assume every animal would have a name. If you've identified it, it must have a name. So we might look to initialize it with a name, and that's fine. So we would say, well, every animal will have a name that is provided via the constructor. And you could have whatever else you would like here, but we'll keep it simple for now. And we might then say that we want to have our interface. So I'll create a new Kotlin class or file. And instead of class, I'll select interface. And the name I'll give is communicate. Communication, I believe, is what I called it in my UNL diagram. So this is the interface called communication. And then from here, I can define what type of behavior I want any class that implements this interface to implement, to have. And I'll do that by listing the set of functions. Now, interfaces in Kotlin, turns out, can do a little bit more than you might be used to if you've used interfaces in Java. But we're not diving into that right now. We're just keeping it simple. We're just going to list the functions. And in this case, we just want one function to keep it simple. So we'll have a function, we'll just call it talk. So every animal can talk, whatever talking means for a specific animal. So we have fun, talk, and that is the communication interface. Back in our animal class, we can now specify that every animal is going to implement the communication interface. And once we specify that we're implementing the communication interface, a couple things happen. Well, one thing really, and that is the IDE is telling me, hey, you have said that you are implementing a certain interface. If that is the case, one of two things have to happen. You either have to provide an implementation for talk, or you need to make this class abstract. Now, for our purposes, since it would be difficult to just have an animal that is not specialized, meaning an animal that you can point to and give a specific name to, it may be very useful to have our animal class, in fact, be abstract. So, in other words, we are not going to define the interface or implement the interface methods here, or the interface functions here, because we don't know what an animal would sound like when it talks. We don't know what sound it would make. So we would not leave it, it needn't to be implemented here. However, any subsequent class that extends or inherits from animal will in fact need to provide an implementation for the talk function, or must itself be declared abstract. So in this scenario, we'll have another class. This will be our dog class. And for now, the only thing I need to specify for dog is that it extends or it inherits from animal. Now I know that animal has a constructor. If we think of the name here as just being the genus, then I know that this is a dog. So it means that I could simply say this extends animal and it's a dog. There are nicer ways to do this, but we can keep it simple for now. Here again, we see the same error message, essentially saying, hey, you're extending animal, that's fine, but animal has implemented or says it is implementing the communication interface. So for this to be complete, you need to have an implementation for the talk function. So I can simply have the IDE help me by putting in the code. So here we are overriding function talk, and this is where I'll put my implementation. Now for me, I'll simply say that our animal can, since it's a dog, one assumes it would bark. That's how a dog would talk. Whereas if I had, say, other animal types, they may make a different sound, or some other output would be printed by my code. But right now, this is essentially a good representation of our UML diagram. We have the animal interface. We have the animal class, rather, that implements the communication interface. And then we have dog that extends animal. Dog provides an implementation for the talk function that's defined in the communication interface, and that was necessary because animal did not provide an implementation. In fact, animal was declared abstract. If animal was not abstract and had in fact provided an implementation for the talk function, then it wouldn't be semantically necessary for us to provide an implementation here, but it would still make sense to do it because however an animal, a generic animal communicates is probably not how a specific dog or a specific animal would communicate. So this dog would have its own mechanism for communication. So the compiler would never complain if we don't provide an implementation, but clearly it is something we would want to do. So going back to our code, let's see how this sort of all works together. So what we want to do now is kind of use these objects. So in my main, I could have a few things. I could have a animal variable, and this animal variable could reference a few different object types. In theory, I could have it be of type animal, or it could be of type dog, although for various reasons this is not the proper way to specify it. Or, depending on how I'm planning to use this reference, it could be of type communication. What's noteworthy is that regardless of the type, in all cases, an instance of dog will suffice. Whether or not I'm looking for a communication object, an animal object, or, of course, a dog object. And this goes back to what we were referencing earlier, which is once we've defined this type of relationship, then as specified here, a dog is of type dog, is of type animal, and is of type communication, i.e. the interface that was implemented. Now, in terms of what that means in practice, well, it comes down to when we start to invoke various functions. So if I just have a reference that's of type dog, and here you're seeing, he's telling me, well, if that's all it is, you don't even need to put the type, but let's keep it there just to be explicit. Then when I'm writing the code animal.talk, the compiler knows exactly which function it's going to invoke. It's going to invoke the talk function defined in dog. However, had I put something like communication here, then it turns out that the compiler doesn't really know until the code is executing which talk function is going to be executed. Because at this point, the reference that it has is communication. We use a reference for the interface, not for the concrete implementation. That is considered proper practice. So we have a type communication, and we are not sure, the compiler is not sure what talk function will be invoked or until it actually gets to that line and is ready to execute it. This is something called late binding, and it is a form, one of a few different forms of polymorphism. The compiler doesn't know which function is going to be invoked. All it knows is that there is a talk function because the interface defines one, but it doesn't know which one it is. So to kind of make that a little clearer, you can imagine that we could have another class. Let's say this one was cat. And this cat is also an animal. And this cat, when it speaks, it will meow. To make it even clearer, let us say that this function main is going to invoke another function, speak, where an animal will be passed in, or let's say a communication object. So when the compiler is looking at this function, it has no idea which concrete object is going to be called, is going to actually have its talk function invoked. So yes, we might decide that here we want to call speak with our animal that we've defined. So it will be a dog, but something else could call this function with a cat or any other communication function, any other communication object rather. So its late binding, i.e. when the program is actually executing, it's only then at runtime will the system know that, oh, we're invoking the talk function for a dog versus the talk function for a cat. At this point, all we know is we're going to invoke the talk function of a communication object. So that's a simple version of polymorphism. Now, in terms of taking this further and kind of touching on the one last piece of the four main tenets of OOP, you could imagine that this implementation wasn't as direct. You could imagine that we have an implementation for a dog or for a cat where instead of simply having the code that it executes to have a dog talk directly implemented inside of the talk function, we could instead have a function called bark, which is basically how our dog communicates. And this function would then print something, it performs some action, and we could make this function private. It's hidden. So the way that our dog communicates is hidden internally. You can't actually invoke it directly from outside. So our main cannot invoke bark. But whenever you call the talk function, that is when we will invoke bark. This is what encapsulation essentially is. It's hiding the inner workings of your class and instead only exposing the known interface. Whether that interface is defined explicitly in a interface, in an interface, or implicitly by simply having a set of public functions, but without a strict interface defined. Of course, the proper way is to specify an interface, but oftentimes for relatively small programs or programs where you don't have a lot of different types that implement an interface, a lot of times people will just have these interfaces be implicit. So there's a spectrum. depending on sort of how rigid you want to follow the rules. And when we execute our code, we can then see what happens. So here, again, my animal, being a dog, should say woof. And if it was a cat, we did not add a private method here, but it should still work. Externally, it works the same. Even though the two classes are implemented differently, you can see that externally, we don't even realize that. The main doesn't know how cat or dog is implemented. All it knows is that there should be a guarantee of a talk function being implemented. So it can safely try to invoke talk, and we get a result, regardless of what the internals look like. So that's sort of a brief overview of inheritance, of interfaces, touching on one aspect of polymorphism, which is what we saw here with late binding, and of course encapsulation, which is hiding the implementation of a class and only presenting the public interface.